but I'll be on it always, always and forever.
Hi, welcome back to the Pink Chemist. So today we will be going over an example on how to find the limiting reactant. Okay. Now, in this example, we're going to go ahead and get right into it. In this example, as you can see, our equation is already balanced. So the first step, which is typically for us to balance the equation, we don't have to do it here because the equation is already balanced. Now next, we are going to list our given and our want. Now this is essential because this is going to help us to set up our railroad tracks the way that we want them. So when we read the question, you begin with 1.20 grams of aluminum and 1.20 grams of bromide. What is your limiting reagent for the following reaction? Now, as you can see, when it comes to limiting reagent or reactant, that's the same thing. You are given two givens, okay? So the first given that we have is 1.20 grams of aluminum. And then our second one is 1.20 grams of Br2. Okay. Then when we read the question, it doesn't tell us specifically what our want is, but if you look here, you would notice that in this particular example, you have your two reactants as you're given, and then you're left with your product. And the only thing that's in your product is AlBr3, which this is a synthesis reaction. Okay. So any other time your want will typically be something that is already given to you. In this case, we are only left with in our product AlBr3 for this synthesis reaction. Okay. So next, now that we set up our given and our want, we are going to now set up our railroad tracks. So this time around, instead of me just having one railroad track, the fact that I was giving two givens lets me know that I am going to have more than one set of railroad tracks. Okay. Now, I also want to note that not only are we going to find the limiting reactant, we're also going to find the theoretical yield, because that is going to be essential to us being able to identify the limiting reactant. Okay. So let's go ahead and set up our chart. So we're going to start with our first given, which is 1.20 grams of Al. Okay. And then in our last box, we're going to go ahead and set it up with our want, which is grams of AlBr3. Okay. So I know that as I'm setting up my railroad tracks, everything must be diagonal so that they can cancel out as far as my units. So I know that if I start with my given, which is grams of Al, that I have to have grams of Al diagonal in my denominator so that it can cancel out. In my numerator, I am going to have mole of Al. Okay. So I'm going to have the mole of the element that it is closest to. That's the way that I like to explain it. And then in my denominator across from Al, I'm going to have mole of Al again across from it where it matches up diagonally so that I can see that that is the units that's going to cancel out. And then in the numerator, I am going to have the mole of AlBr3. Okay. And then in this box, I'm going to have mole of AlBr3. Okay. So as I look, grams of Al and grams of Al, they match. Moles of Al, they match. Moles of AlBr3, they match because they're going to eventually cancel out, and I'm only going to be left with grams of AlBr3, which is what I want. All right, so now as it comes to filling in my chart with my numbers, anytime that I have mole over grams, my mole is going to be 1. When I see the unit grams, that means that I have to go to the periodic table and use the periodic table to help me to find my molar mass. Now, in this instance, AL, we only have one AL, so 1 times 27 is going to be 27. You will need to use your periodic table in order to get the atomic mass to fill that in. Anytime I have mole over mole, my moles will be filled in by looking at the coefficient from our balance equation. So the coefficient in front of AlBr3 is 2. So that lets me know that I have 2 moles of AlBr3. And then my coefficient in front of Al is 2. So that is what I'm going to plug in for my moles. Now in my last box here, I have grams of AlBr3. So now I have to also separate that. So I'm going to go ahead and do that at the top. I have Al and then I have Br. Okay. I have 1 Al and 3 Brs. Now this is me finding the molar mass. Al has an atomic mass of 27 and Br has an atomic mass of 80. So 1 times 27 is 27, and then 3 times 80, let me go ahead and do the math, is 240. All right. Now when I add these two numbers up, 27 plus 240, I am going to get 276, and that is my molar mass for grams of AlBr3. And when I have grams over mole, my mole is always 1. All right. So now I have to actually do the math going across. So now I'm going to multiply 1.20 times 1 times 2 times 267. Okay. So now in my numerator, once I do that, I have 640.8. I'm now going to multiply my denominator, which is 27 times 2, which gives me 54. Now, once I get this number, I'm going to take that 640.8 and divide it by 54, and that gives me 11.87. I'm going to go ahead and round 2 places after the decimal. And then once I go ahead and cancel out my like units, I'm left with grams of AlBr3. Okay. So that is my first value for my first railroad tracks. Now I'm going to do a second railroad track. Okay. Okay, so let's go ahead and start with our second railroad track. Okay. For our second given. So what we're going to do is make sure that you have space, because if you don't have enough space, then it will cause for you to kind of mess up. So let's go ahead and try this here. All right. So your second given is 1.20 grams of Br2. And then your one is still going to be the same, grams of AlBr3. Okay. Now you got grams of Br2 here. Then you got mole of Br2. Got your mole of Br2 here, so it can cancel out. And then you're going to have your mole of AlBr3. Then your mole of AlBr3. All right. Now that you have this set up, now let's go ahead and set up our numbers. You got to find the molar mass. So you got 2 Br, so 2 times 80 is 160. Let me fix that. It's 160. All right. And then your mole of AlBr3 is 2. And then your mole of Br2 is 3. And then your grams, you've already did this. So your grams of AlBr3 is 267. And then your mole is 1. So your numerator is pretty much going to be the same as what you did before, because your numerator in your first set of railroad tracks is the same thing as your numerator in your second. So we got 640.8. Now the only thing that we have to do now is do the math for the denominator. So we're going to multiply 160 times 3 times 1, which gives us 480. Then we're going to divide it. 640 divided by 480, it gives us 1.335. Okay, the 1.335. Okay, and then with your units, you're gonna go ahead and cancel out, and you're gonna be left with grams of AlBr3. Now this is important because now that we've did the works for the two tracks, now we have to compare. Okay, we're going to compare our answers to be able to identify our theoretical yield and our limiting reactant. Now, your theoretical yield is going to be the smallest number out of the two. So the values that we have is for the first one, which is 11.87. And then for the second one, we have 1.335 grams of AlBr3. Out of the two, the 1.335 grams is our smallest number. So that is going to be our theoretical yield. Okay. Now, in order to identify your limiting reactant is a compound. It is not a number. Your theoretical yield is an actual number, but your limiting reactant is going to be a compound or the element that you started with, okay? Now, as you notice, this is called limiting reagent, okay? Your limiting reagent is the same as your limiting reactant. It's the same thing. So when we look at our reactant, which is Al and Br2, those were the two elements that we were given. Okay. So you want to go back to the smallest number, the smallest value that you had, which is that 1.335. You want to go back to that 1.335 and you want to go back to the given, which is right here. That given element is going to be your limiting reagent. So the element that we started with to get that small number was Br2. That is the reactant that we use to get our theoretical yield, which will now be considered our limiting reactant. Okay. Now, that will leave for our largest, the one that was our largest number, which was the 11.87. That would then mean that that reactant that we started with, which was Al, that will be considered our excess reactant. And in our next video, we will get into how to identify our excess reactant. So I'll see you in the next video.
Don't play with it, don't be dishonest. Ay, still not understanding.